So this is the last talk for today. We have Travis Mandel from University of Oklahoma, and we will talk about tropical Theta functions for cluster varieties.
Hey, thank you. Thank you to the organizers for putting this conference together and inviting me to speak. So I'm excited to tell you today about some work in progress I have going joint with Man-Wei Chung, Tim McGee, and Greg Muller. As I said, this work is still very much in progress, but we have a number of results I'm excited about. So I'm happy to have a chance to tell you all about what we've come up with so far. So I'll start by giving you a little basic background and telling you what I view as our main theorem so far. Mainly because it's kind of the central theorem. We have results going in a bunch of different directions, all kind of building off this one thing or closely related to this one. So for the purposes of this talk, I'm calling it the evaluative independence theorem. I made that name up over during the talk, so maybe it'll have a different name later, but call it that for now. So start with a quick review of the basics of what a discrete valuation is. So a discrete valuation, denote val, is a function mapping a field K. For us, that'll be a function field of rational functions on some variety, on a cluster variety. Maps K to the integers union infinity. And valuation takes a product. The valuation of a product is the sum of the valuations. Valuation of a sum is greater than or equal to the minimum of the valuations of the terms. And valuations infinity if and only if the thing you're taking valuation of is 0. So these hold for all x, y in your field K. And the main example we'll care about is if you have some, say, a variety y, some prime divisor d in y, and K is your function field on y, then we can take val d, meaning that the divisorial valuation for d, which just takes a rational function f to the order of vanishing or pole of f along d. Or if f has a pole along d, you get a negative number that's the order of pole, or negative the order of pole. If it has a 0 along there, you get some positive number. And the property I want to emphasize is this one. In general, the left side might only be greater than or equal to the right side. And basically, the reason it could be greater than the right side is you might have stuff cancel. Maybe x and y both have an order, say order 5 pole along d. But when you add them together, those kind of worst terms, the highest order poles, cancel out, and you end up with a less bad pole. So kind of the key thing I want to look at today is cases where you don't have cancellation, and we can actually say we have an equality here. And that ends up being a very useful property. Okay, so let's start with the simple toric varieties cases. So in the toric setting, we have some lattice n, so that's z to the r for some finite number, positive integer r. So that this is our co-character lattice. We let m be the dual lattice, so that's the character lattice. I don't know if I actually use this notation later. Maybe I'll skip that. Yeah, sure. I'll mention this. So let T sub n be the algebraic torus n tensor C star, and you can think of this as spec of C adjoined M. So C adjoined M is the Laurent polynomial ring with exponents in the lattice M. So it's C adjoined. You have a monomial z to the m for each element of the lattice, modulo these relations that z to the m1, z to the m2 is z to the m1 plus m2. Now, remember from toric geometry that if you have an element of the lattice n, a non-zero element, we can take the ray generated by that element, and this ray, any ray of rational slope like this, determines a boundary divisor, call it d sub rho sub n, or just d sub n. So this is a boundary divisor that partially compactifies this torus. Right? You can take the fan, or if you think of this ray plus the origin as being a fan, you take the corresponding toric variety, that will be this torus plus some additional boundary divisor, calling that boundary divisor d sub n. And you can ask about the valuations along that boundary divisor. So we have this divisorial valuation, val d sub n, and I'll let val n denote basically val d sub n times the index of n. So in the index of n, that's the biggest positive integer that you can divide n by and still get something in the lattice, as opposed to like in the lattice tensor Q. Or in other words, n is equal to the index of n times a primitive vector n prime. Primitive meaning it's not a positive multiple of anything else in the lattice. Okay, so we've defined this valuation. This is a discrete valuation on our function field. And so on a field of fractions of C joined M. And it turns out val n of z to the m, of the monomial z to the m, is just the dual pairing between n and m. I'm using these angled brackets to indicate the dual pairing. So m is hom of n to z, pair elements get an integer. So yeah, val n of z to the m is just that dual pairing. And in fact, more than this, if you take val n of any Laurent polynomial, so any element of this ring, that will equal just the minimum over all the terms of pairing here of the dual pairings. Or in other words, it's the minimum of, so by this line, these dual pairings we can think of as val n of z to the m. So in other words, in this setting, the valuation of the sum is equal to the minimum of the valuations of the terms, as opposed to greater than or equal to, like we saw here. And this is a pretty simple property, but it's actually, I think, something we take for granted in toric geometry as being something that we use all the time. The reason that you have a monomial basis for affine toric varieties is because of this property. The reason you have monomial bases for toric line bundles is because of this property. So this actually gets used all the time. And what we're going to see is that the same thing holds for cluster varieties with theta functions. And so then a lot of toric constructions carry over to the cluster setting. Okay, so I call this this property the evaluative independence theorem, VIT, at least for the purpose of this talk. So let's say that Y is a cluster variety. So it could be a toric variety or something more complicated where you do some non-toric blowups or glue kind of a bunch of tori together. So say Y is a cluster variety. Yeah, again, with cluster varieties, you have a lattice n, like in the toric setting. You just take, so cluster varieties are built by gluing a bunch of algebraic tori together. You can just take this lattice n for any of those tori and identify that with what I want to view as kind of the tropical integer points for Y. So we have this lattice n. And again, this will parameterize divisorial valuations, val n, like before. And then we can apply these valuations to functions. And we also have a dual lattice m, and m will parameterize theta functions on Y. So I'm not going to review the whole construction of theta functions. I think hopefully that's covered in some other talks in this conference. So we take this dual lattice m, and this will parameterize theta functions on the cluster variety Y. Using these scattering diagram broken lines methods. Now our kind of main or central theorem is that under basically some mild hypotheses on Y, the value val n of a linear combination of theta functions is equal to the minimum of the valuations of the theta functions that appear in that sum. So in other words, just like with monomials, there's no cancellation, and valuation of the sum is actually the minimum of the valuations. Valuation of a sum of constants times theta functions. Okay, and now just like in the toric setting, we can apply this to do a bunch of nice constructions. So talk about how this can be applied to compactifications of cluster varieties, line bundles on cluster varieties, and then certain operations that you might do on freezing stuff for a cluster variety. I'll talk about that in a few slides. A little notation though. So given an element n of the lattice n, you've seen this determines a function val n on functions. We can also think of val n as a function from the lattice m to the integer z, which, given some element m of the lattice, maps you to val n of theta m. And maybe I should mention, I believe all this stuff, I need to double check, but I think all this stuff will hold even without the full Fock-Kontrov conjecture. So in other words, where some theta functions are actually infinite Laurent series instead of Laurent polynomials, you just have to interpret, you have to allow val n of theta m to maybe be negative infinity. So you have to generalize what valuation means a little bit, but I do think everything should carry over to that setting as well. So yeah, given some element n of this lattice, we get this function val n on your lattice m like this. And dually, given something in m, we define theta m trop to be essentially the dual function on n. It takes an element n of the lattice n to val n of theta m. Okay, so an element in one lattice determines a function on the other lattice. All right, now I'll use that notation a lot for the rest of the talk. So a corollary, your first corollary of that kind of valuative independence theorem is this statement. So suppose that you have a theta function basis for the ring of global regular functions on Y. So this frequently holds for cluster varieties, but if the full Fock-Kontrov conjecture holds, you have this. And there's some nice criteria for when that holds. That's that Y bar be one of these partial compactifications of Y. So basically Y bar is equal to Y union a bunch of boundary divisors d sub n, some d sub n for each n living in some finite set f in n. So I'm saying f is some finite set of primitive vectors. These correspond to some boundary divisors, and we just glue all of those on. We might also glue on some additional higher codimension stuff, but this is what we care about. And I'm going to let S sub y bar to be this subset of M. So basically for each element of F, so for each of these boundary divisors, we're going to take only the elements M which have non-negative valuation on that boundary divisor. And then we intersect this over all those boundary divisors. So basically these are the M's such that the corresponding theta functions extend over Y bar without having poles on any of these new boundary divisors. That's what these conditions are saying. To take the M such that the theta functions don't have poles on any of these DNs. And the claim is that these theta functions form a basis for your compactification for Y bar. So in principle, just because in principle, if you take all the theta functions that are still regular on the compactification, they might not necessarily form a basis, at least a priori, because you might have some regular function which is a linear combination of theta functions, but two of those theta functions individually maybe have poles on some of your boundary divisors, but you add together some combination of them where those poles cancel and it ends up being regular. But by the valuative independence theorem, that doesn't happen. Okay, so given any function f on this compactification, you can restrict it to y. By assumption, we can then express it as a linear combination of theta functions. And each theta function appearing here must be in the set S by bar. In other words, it must itself be a regular function on Y bar. Because if any of these had negative valuation on some d sub n, then f would also have negative valuation. That's what the valuative independence theorem tells you. In other words, f would have a pole on one of these dn's, so it would not be a global regular function. Okay, so this immediate corollary is that if we have a theta function basis for y, we get theta function bases for all these nice compactifications of y. And we can generalize this to make a similar statement about line bundles. So for y bar as before, let's let W be some divisor supported on the boundary. So it's a sum of an dn for an's being some integers, dn's being some of these boundary divisors. And we can look at the theta m's, the set of theta m's, which are global regular functions of the corresponding line bundle. You take the line bundle O of W, the global sections of that are the functions the functions such that val n of them is greater than or equal to negative an for each n. To be a global section of line bundle associated with some divisor, you just need the valuation along each dn to be greater than or equal to negative that coefficient. And so the claim now is that the theta functions, which are global sections of this, form a basis for the global sections. And it's just the same argument as in the previous case, essentially the same argument that if you have a function which is, which is a linear combination of theta functions, and it's a global section of this, then each theta function of pairing must itself be a global section, or else, or because the evaluative independence theorem says there's no cancellation of poles. Okay, so now one thing that previous theorem is missing, or one slight drawback of it, is that it only seems to apply to line bundle support on the boundary. Right, my W is a sum of boundary divisors here, and I'm looking at O of W here. But with cluster varieties, you can have line bundles which are not isomorphic to one support on the boundary. O of W for W sum of boundary divisors doesn't give you all line bundles. So remember, a cluster variety can be viewed as you start with a torque variety and you do some non-torque blowups of stuff on the boundary. And then you get these exceptional divisors when you do those blowups. And you can show that every line bundle is isomorphic to one support on the boundary plus the exceptional divisors. So if we could extend to allow that W to include exceptional divisors, then we could actually get theta bases for all line bundles. So in fact, we can do that. So let's that X phi be a fiber of the cluster X variety. So this is, for example, like a Lewinga pair, or a Lewinga interior is something that shows up as a fiber of a cluster X variety. And that X phi bar be some compactification of that. So that's like a Lewinga pair. We're including the boundary now. And that A phi bar be the corresponding partially compactified cluster A variety with coefficients. So there's always this cluster A variety mapping to your cluster X variety. It's kind of it's a torsor over some special fiber of your cluster X variety. But if you deform your coefficients of the A variety, you can get torsors over the other fibers of the X space. So you can get a torsor over X phi bar. Theorem of mine from a few years ago is that the global sections on A phi bar are equal to this. You can take the direct sum over over a bunch of divisors W, and then for each of those W's, you take the global sections of the corresponding line bundle. And you can put a ring structure on this, and that ring is isomorphic to this ring of global regular functions. And this direct sum here is over all divisors W, which are supported on the boundary and exceptional divisors of X phi bar. Oh, I should have this should be X phi bar here. Yeah, sorry, X phi bar. So now we're allowing W to include exceptional divisors. And then furthermore, the sum is here. So there's a natural torus action. So A phi bar is some torsor over X phi bar. There's a torus action that you quotient by to get from A phi bar to X phi bar. And the summands here are weight spaces for that torus action. the reason that matters is that the theta functions are eigenfunctions for that torus action, or they live in these weight spaces. So in other words, you have a theta function basis for each weight space. So you can hope if you have a theta function basis on this side, does it automatically give you a theta function basis for each sum inter? And the kind of missing ingredient for that is the evaluative independence theorem. Actually, no, that's not the missing ingredient. Sorry, no. Automatically, if you have, so just from this statement, if you have a theta function basis on the left, that gives you a theta function basis for each sum inter. And so then the question is, how do you know when you have a theta function basis on the left? And that's what we get from the evaluative independence theorem. So basically it says that if you have a theta function basis for a phi, we automatically get a theta function basis for compactifications of a phi. So for a phi bar, and so then in the setup of that previous slide, we get a theta function basis for global sections of any of these line bundles. So then, assuming that you have theta function bases here, which should at least be true when the Falk-Armstrong conjecture holds for a prin, which happens quite often. Then you get a theta function basis for every line bundle. Now you do have to choose an isomorphism of your line bundle with one that's supported on the boundary plus exceptional divisors. And I don't know to what extent the basis depends on that depends on which line bundle you choose in the isomorphism class. There could be more than one way to represent a line bundle as a sum of boundary and exceptional divisors. So I don't quite know, how often the theta function basis is actually canonical and how often it depends on some choice there. But at least if you have line bundle support on the boundary using what we had a couple slides ago, you get a canonical theta function basis. And I think for mirror symmetry reasons, I believe canonical basis is expected at least for ample line bundles. So this should give a construction for that. Okay, so so far, these applications I've talked about have all been, we have a theta function basis for regular functions on our cluster variety, and can we use that to get a theta function basis for some compactification or line bundle on the cluster variety? So now I want to look at using theta functions on one cluster variety to get theta functions on a different cluster variety, one that's maybe a bit more complex. So a cluster variety, yeah. Sorry, so I can't see if someone's talking. So yeah, let me know if there's a question or something. Okay. So we construct a cluster variety from the data of a seed. Oops. From the data of a seed. So a seed is basically it's the data of your lattice n, and then the directions that tell you essentially what non-toric blowups you're doing. But then some of these directions you might freeze. You say you don't do a non-toric blowup in this direction. Maybe you just keep track of the extra vectors that you call frozen vectors to maybe identify what boundary divisors you're interested in. So in other words, you might have some frozen vectors that you don't allow yourself to mutate. Let's let S prime be a new seed that you obtain by unfreezing some of these indices. So we take some of the frozen vectors and say that they're no longer frozen. We can actually mutate them. We actually do some corresponding non-toric blowups. That's that Y and Y prime be the corresponding cluster varieties. Assume they both have theta function bases. Then say we have a theta function theta m on Y. Then if we know that theta m extends to a global regular function on Y prime, then automatically that extension is still a theta function. Okay, so the most basic example is if you have what's called a global monomial. So if you freeze every index of your seed, then your cluster variety is just a torus. And the theta functions on a torus are monomials. And if any of those monomials extends to a global regular function when you unfreeze, that global regular function is called a global monomial. And global monomials are always theta functions. They're always theta functions. That was shown in Grossack and Kilkinsevich's paper on theta functions for cluster varieties. So this theorem gives a generalization of that. It's anytime any theta function extends to a global regular function, automatically that extension's a theta function, not just for monomials. So the proof sketch, here's a sketch of the proof for principal coefficients cases. Other cases are derived from this one. And it just uses the evaluative independence theorem. The idea is, so theta m tilde, so that's some extension of theta m. So if you pick some cluster, it's given by the same Laurent polynomial there after you unfreeze as it was before. So in other words, theta m tilde has the same valuations as theta m, because the boundary divisors look the same as before. You can just restrict to the cluster variety you had before. Your valuations will be the same. On the other hand, theta m, so let's let theta m prime be the theta function on y prime corresponding to m. We want to show that theta m tilde equals theta m prime in order to show theta m tilde is a theta function. And just by, so theta m tilde is m pointed, it's equal to z to the m plus some kind of higher degree stuff. It follows from that theta m tilde is equal to theta m prime plus some linear combination of other theta functions, all of which have higher degree. So this is basically saying they have higher degree in a certain sense. Now, if these two were not equal, well, if they're not equal, then what that means is that theta m prime, so when you unfreeze stuff, you add new walls to your scattering diagram. And so if these are not equal, what's happening is theta m prime is picking up new monomials because of these new walls, producing new broken lines. So theta m prime has more terms. So if these are not equal, what's happening is that theta m prime will have a lower valuation on some n than theta m did. So then theta m tilde, since theta m tilde is theta m prime plus some additional stuff, the evaluative independence theorem says that the valuation of theta m tilde is less than the valuation of theta m prime, or sorry, it's less than or equal to the valuation of theta m prime, hence less than the valuation of theta m. And so you get this contradiction. So in fact, these two must actually be equal, and that proves that the theorem. Okay, so why is this useful? So I want to give kind of the motivating example that made us look into this. So an early, still very important example of cluster varieties is Falcon-Goncharov's construction of cluster structures on certain moduli of local systems. So that's that sigma be some triangulable marked surface. So it's a surface with like maybe with some boundary and with a bunch of marked points, certain conditions on where marked points have to be. You need one on each boundary component, things like that. Then certain moduli of local systems on sigma, you can form a moduli space called Y sigma. And Falcon-Goncharov showed this as the structure of a cluster variety. So let's say that you understand maybe Y sigma for your surface sigma, and you would like to understand the moduli space for some other surface sigma prime, where you construct sigma prime by taking two boundary edges of sigma and gluing them together. Okay, so well, two boundary edges or maybe a bunch of boundary components of sigma, and sigma does not have to be connected. So you can, if you're really interested in sigma prime, you can cut it into a bunch of pieces and then call that cut up surface sigma, and then you can reconstruct sigma prime by gluing these boundary arcs. And what this corollary says is that theta functions for sigma give you theta functions for sigma prime. And that's basically because when you glue boundary arcs together, that can be understood as you're kind of identifying certain frozen indices, which that can be the effect of that on theta functions is easy to understand. It's kind of taking a quotient of your scattering diagram. So gluing boundary arcs, you identify frozen indices, and then since they're no longer on the boundary, you unfreeze them. And the unfreezing doesn't mess up theta functions because of the previous slide, because of this result. So theta functions on this cup surface give you theta functions for the glued surface. So I have a paper, hopefully will be done soon with Fan Shin. We're working on finishing up, but we show for the case of SL2 local systems or PGL2 local systems that the bracelet basis coincides with the theta function basis. And when we use this gluing technique that if you want to understand theta functions for one surface, you can cut it into pieces and understand the simpler ones first. But we didn't have this corollary. We've been working on that paper longer. We're not relying on this result. So we had a proof there that doesn't generalize. We're kind of stuck. How do we get to higher moduli of local systems? So this corollary kind of gives a foothold to start looking at SLN or PGLN local systems, these higher cases. So that'll hopefully be useful for future stuff. Okay, so now I'm going to go back to, are there any questions at this point, actually?
Is there any chance that this property, this evaluative theorem, can that characterize the theta function basis? Is there any chance like that?
Let's see. So I don't, yes, I've wondered to what extent you can use this to characterize theta functions. I don't think that's enough, but maybe if you kind of use that with some other stuff in some clever way, maybe there's something you can do, but I don't know how to do it with just, I don't know how to do it, I guess. It does seem like a strong property, and maybe that plus some other properties might be enough, but I don't know something at this point. I think there is a paper from a few months ago on polytope bases, which I haven't looked closely at it, but it seems like it would maybe be something related to this, but I don't know at this point. So I want to, anything else? All right, so I want to talk about kind of give a sketch or a rough idea of how we prove this evaluative independence theorem by basically talking a bit more about tropical theta functions. So let's focus on the case of the cluster A variety. So to understand theta functions on this, you consider a scattering diagram whose initial walls look like this. So this lives in M sub R, M tensor R. So EI perp lives in there. That's the support of your initial walls. Then your initial scattering functions look something like this. 1 plus z to the, see, B is some skew symmetric form on the lattice N. It's part of your seed data. And if you put EI in one of the entries, you can think of that as something in the dual lattice. So we get these binomials. These are our initial scattering functions. Now, from this, take this as your initial scattering diagram, build a consistent scattering diagram. Then your theta functions are defined as certain sums of broken lines. So given some generic Q in M tensor R, theta MQ is defined to be the sum over all broken lines gamma with ends M and Q of basically the final monomial on that broken line. Final monomial C gamma Z to the M gamma. And so having ends M and Q means that the broken line comes in from direction M with initial exponent M, and it ends at this point Q. This is the final attached monomial. And if Q is in what's called the positive cone, then this Laurent polynomial here you view that as the theta function expressed in your initial cluster. So in kind of your initial algebraic torus. And to get, to understand the valuation of your theta function, val n of theta m, then you just look at the minimum over all, you look at the minimum over all the terms of pairing here of the dual pairings of the exponents with your n. So in other words, theta m trop can be understood as you take the minimum over all broken lines gamma with n's mq of m sub gamma viewed as a function from n to z. And this is clearly a piecewise linear function, and that will be theta m trop. Is there a question? So each of these m gammas is a linear function. So this minimum of m gammas is a piecewise linear function. So that's our theta m trop. Now, the thing that makes this formula complicated is, well, one thing is you could be dealing with many broken lines there, and it can be kind of hard to get a handle on them. And how do you know which broken line is giving you the min without looking at all of the broken lines? So it turns out the broken line which gives you the minimum will always be what we call taut. So we say a broken line gamma is n taut if whenever it crosses a wall, the bend it takes is either maximal or minimal. So you have some choice of how much broken line bends when it crosses a wall. It's some integer multiple of this exponent that's attached to the wall. And we choose the bend that is either bending as much as possible or as little as possible, or not bending. And the one you choose is the one which minimizes this dual pairing between n and the attached exponent immediately on the new side of the wall. So it's like, so our goal is to, on the final straight segment of gamma, minimize this dual pairing. And so if you're trying to do some greedy construction for what you hope would minimize that dual pairing on the final segment, what you might try and do is at each step do the thing that minimizes the dual pairing. And then this proposition says that works. This kind of greedy construction really gives you a gamma that minimizes the dual pairing. So the broken line gamma, which determines this minimum from the previous slide, so this minimum, that broken line will always be n taut. Okay, and so the proof, the basic idea is we generalize broken lines so that instead of the bend being an integer multiple of the exponent attached to the wall, we allow rational multiples. And by allowing rational multiples, our broken lines can be continuously deformed. We can take some small deformation of them. And then if we show that if you take a small deformation towards, like if you're not n taut and you deform a little bit to make it closer to being n taut, that will reduce this dual pairing. So therefore, you can't get a local minimum anywhere. You can't get a local minimum unless your broken line is taut. So then, therefore, you can't get a global minimum unless it's taut. So the global minimum must be attained for some n taut broken line. Okay, now a couple quick corollaries of that. If you know the slope of theta m trop at some generic point n, that the slope at this one generic point is enough to determine what the index m is. And the reason is, if you know the slope at one point, the slope at this point n, that slope is just the data of that final exponent m gamma for the broken line gamma that gives you the min. The broken line gamma that determines that minimum of these dual pairings. So once you know m gamma, you can start at this final endpoint n and start reconstructing gamma by tracing backwards. So we have this final point n, maybe I should have called this Q. I think that would have been a better name, but oh, sorry, no, said this wrong. So we said this wrong. We have our final endpoint Q that our broken lines are ending at, and at that point Q, we're taking the final exponent and taking the dual pairing of that with n. And so if we know this, the slope, so we know m gamma, you start at Q and start working backwards, kind of moving in the direction m gamma. And then whenever you cross a wall, you want to know how to bend on that wall, and you just choose the bend that will make this broken line n taut. This n tautness tells you what the bend has to be. And so using that, you can reconstruct the entire broken line, and then the direction that it goes to infinity in must be the direction m. It's this index m we're interested in. So you reconstruct the broken line to figure out what m was, what the initial direction was. So that proves this first corollary. And then another way to state that, or another way to think about that, is if you have two, if you know that theta m1 trop is equal to theta m2 trop on some non-empty open set, then you must have m1 equal to m2. You must be tropicalizing the same theta function, because if they're equal on some non-empty open set, then they must have the same slope at generic points in that open set. So the previous corollary says that the index is totally determined by what's going on that open set. Okay, so now, I told you I wanted to sketch the proof of this evaluative independence theorem. So say we take a linear combination of theta functions. So remember what this theorem says is that val n of this linear combination is the min of the valuations of the individual theta functions. So we want to show we have equality. In general, because this is a valuation, we know the left side is greater than or equal to the right side. So we just need to rule out the case where the left side is greater than the right side. So suppose that the left-hand side here was greater than the right-hand side. Well then, in order to get a strict inequality like this with divisorial evaluations, the only way that can happen is if some stuff cancels, right? Kind of the things giving you your worst poles or lowest order zeros cancel, and so then you end up with a higher valuation. So for that cancellation to happen, you would have to have two or more terms over here, which have the same valuation. You'd have to have two more terms with val n being equal. So you'd have some two terms here where val n of theta m1 equals val n of theta m2, with m1 and m2 not being equal. By those corollaries on the previous slide, that doesn't happen for generic n. Right? If two tropical theta functions agree on an open set, then you're tropicalizing the same theta function. So this can't happen for generic n. So this equality holds for generic n. Right, for generic n, you get this equality. And then you can immediately extend to all values n, because tropicalizations of functions are piecewise linear. In particular, they're continuous. So you can't just have some discrete or lower dimensional or something set of n where this jumps and you get strict inequality, because then then it wouldn't be continuous. You'd have these jumps, so it must actually be equal for all n. So that implies then this evaluative independence theorem. Right. So any questions at this point? Okay, so there's a couple more quick applications or related results that I want to mention. So these are broken line convexity and theta reciprocity. So there's this notion in GHKK, it's called convexity along broken lines. Actually, they might have changed the name. It might be min convex or something. I'll call it convexity along broken lines. So let's let psi be a piecewise linear function from M tends to R to R. We say that a function like this is convex along broken lines if for all broken lines gamma, given a broken line gamma, you can take d of psi at any point on gamma, and so that's some differential. Pair that with the tangent vector to gamma, gamma prime of t, and that pairing d psi of gamma prime should be non-increasing as you move along gamma. And this is a useful result, useful thing. Or sorry, this is a useful property. So yeah, it's used in GHKK to prove certain cases that theta functions actually give you a basis for the ring of regular functions, or that you can get sections of some ample line bundles out of this. So using our techniques, we get a lower, a much simpler lower tech proof of this result of Sean Keogh and Tony Yu. Basically, if f is any linear combination of theta functions, then f trop is convex along broken lines. So GHKK conjectured that if you have any regular function, its tropicalization is convex along broken lines. So if you know that you have a theta function basis, your regular function is a linear combination of theta functions, and then we find that automatically then it's convex along broken lines. So Keogh and Yu showed this using these rigid analytic geometry methods, and the proof's very cool, but it is very dense and kind of hard to grasp. So we understand this just dealing with combinatorics of broken lines. And then last result I want to mention, we're calling theta reciprocity. So this construction of the theta function basis for your cluster variety, it's a mirror symmetry construction. So you should also have a mirror dual construction, which gives you theta functions on the other side. So there is a construction like this, given any n in your lattice n. Yes? Okay. So given an element of your lattice, n, you get a theta function theta n. So remember, before we were looking at theta m's, now we have theta n's. And then given an element m of that dual lattice m, you get valuations of functions on your mirror space. These m's give you divisorial evaluations for the mirror or the kind of dual cluster variety. You get these valuations. And so now we kind of have two ways to take an element of n and an element of m and pair them together in some canonical way. You can either take val n of theta m, which if you want, you can think of that as theta m trop of n would be another way to write that. Or you could take val m of theta n, just kind of switch which side you're viewing as the mirror. And we find that these two are equal, that whichever side you view as the mirror, this dual pairing between n and m is the same. It doesn't matter which side you're viewing as the mirror space. So it's some sort of, this seems like some sort of mirror symmetry result. We don't really have a geometric interpretation at this point for why it should be true, but it had been conjectured a while ago. I proved the Louis-Angle pairs case of this in my thesis, but could not extend to higher dimensional cases until now. So, basic corollary then is that any property of tropical theta functions is automatically also a property of valuations and vice versa. So for example, that val n can be viewed as theta n trop. And so then we know that that this gives you an integral piecewise linear function on M tensor R, which is convex along broken lines. And so then we get all these properties of valuations for free. And then we can start doing constructions like using these val n's to construct broken line convex polytopes. So, a convex polytope, any straight line between 2 points is entirely contained in the polytope. Broken line convex, any broken line between 2 points in the polytope is entirely contained in the polytope. So we can use these val lines to reconstruct polytopes like this, and then you can start doing some toric geometry type of constructions, where given a convex polytope, you can build some ample line bundle with the basis of theta functions in this case, and so we can start developing constructions like that. So, kind of summarize the point of our results and the extra shot of our paper is that by studying these tropical theta functions and understanding their properties, things like this evaluative independence theorem, we're able to take a bunch of constructions from toric geometry, kind of a bunch of the standard techniques that are used there, and extend them to the setting of cluster varieties and start building these new combinatorial techniques that weren't previously known in the cluster setting, and start using them to prove new results there. So I guess, that's it for what I want to say about this. So thank you.
Okay, this time, Travis. Question from this room?
So can you illustrate this notion of which broken line gives you the minimum on an example?
Sure. I can try. So let's say that our n is the vector maybe -1, -1. I'm going to identify n and m using the dot product. Let's say the initial walls of our scattering diagram in M look, well, just keep it simple, I guess. Let's say it looks something like this. So we have 1 plus z to the e2 dual, 1 plus, actually, it should be negative e2 dual. No, sorry, that's positive. Then 1 plus z to the negative e1 dual. Then on this one, the function is 1 plus z to the minus e1 dual plus e2 dual. So this is the scattering diagram that you would get for just this basic A2 quiver. And so for this n, let's see, we want to minimize basically the dot product of the final monomial with this vector. So now consider a broken line. Let's see. Let's look at don't really know what a good one is. Let's say theta sub 1, -1. So we have, or we should pick a point Q here. So there are two broken lines that end there. This broken line and this one. And so with the bottom broken line, when we bend here, we're bending, let's see. So we're bending, which way is it? Bending away. Maybe I should say it like this. So the attached monomial here is 1, -1. And this one is 1, -1, and then 1, -1 plus -1, 0. So that's the exponent for the attached monomial. So we're adding that vector when we bend. So this is 0, -1. So basically, with this bend, we've added something that has positive dot product with this n, add something that has positive dot product, so that would increase the dual pairing. So this one would not give us the min. So so this top broken line must be the one that gives you the minimum. This would be the top one, and it's the one that gives you the minimum. The minimum dual pairing. It's kind of trivial in this case because there's only one bend. So of course, for that one bend, you want the one that the broken line that bends in the way that will minimize things. But you could say, suppose we had more arrows, can even do a bunch of arrows like this, then our scattering diagram gets much more complicated. You end up with infinitely many rays, and you get some dense cone. And now it should still be the case that if you bend on any of these rays, you would be adding something. Let's see. Actually, not any of those rays. So if you bend on any of the rays in the top half there, at least, I think those would be the ones that have, if I'm doing this right, positive dot product with the direction -1, -1. And so those bends would not be end taut. So then that tells you that that even in these cases you won't want broken lines that bend. Sorry, that broken lines that bend on any of the rays, at least on any of the rays in the top half there. My guess is that rays in the bottom half, if you bend on those, you probably won't be able to reach the top half. So you again end up with, I think you would end up again with this broken line being the one that minimizes that dual pairing. So you then know what theta 1, -1 trop of n is from this.
So you don't need to compute the set of broken lines to compute the value.
Right. You need to know the taut broken lines, and I'm hoping that I think there probably are not other taut broken lines that reach the positive chamber even in these cases with more walls there. I'd have to think about it a bit more to be sure. It shouldn't be hard to show if it's correct though. But right, yeah, you don't need to understand all the broken lines, only the taut ones. And then one useful thing about that is you can reconstruct the taut ones because you know what the bends are. There could be more than one taut broken line, but if you know the final exponent, then you know what the whole broken line was. And also, you can start to you can start to say a bit more about the tropical theta functions. So they're convex along broken lines, and you can say when these piecewise linear functions bend, what those bends should look like. They should look like some taut kind of some taut bend in some sense. Let's see. I'm not sure how to say it right, but.
Okay, any other question from the room?
Oh, actually, something quick. One quick useful thing I should have said in these examples. If you're looking at a tropical theta, so in these rank 2 cases, these two-dimensional scattering diagrams, if you're looking at kind of the fiber where some tropical theta function is negative, the top bend will always be the one that bends as much as possible. Let's see if it's negative as much as possible towards the origin, and if it's a positive fiber as much as possible away from the origin. So that's kind of a nice way then to understand what top looks like. So in this case, this is a place where this tropical theta function would be positive. Or no, I guess it must be where it's negative because we don't want to bend. Right. So we don't want to take the bend there. So just another way to think about this. Actually, I guess that product would be 0, so that's maybe not the best example, but sorry. There are some geometric ways to understand this. So I'll stop.
Okay, any question from the Zoom room? Yeah, let's thank Travis again. That's it for today.